Morning, everybody. We'll start in just a couple minutes here. Going to give folks a little more time to join us if they are trying to do so. All right. Tony, are you able to hear me now? I think I'm about ready to get kicked off here. Perfect. Looks like we got a Hal internal training plus Andy today, so really appreciate all you guys joining. I'm sure some more folks may join as we go through the webinar here. So we should be able to see. All right, good. The audio is working. You guys are seeing the presentation here clearly as well. I'll assume yes. All right, so let's go ahead and get this kicked off. Really appreciate everyone joining us today over at Hal Extraction and other members of the cannabis industry. And so today's topic is a continuation of the last webinar we did, where we're going to move beyond the initial extraction process. So last time, for folks that don't know, they may just be joining us, we discussed hydrocarbon extracts, ethanol extracts, CO2 extracts, and then mechanical or rosin extract processes. Did a nice little high-level comparison of kind of what goes into each process, benefits, and the let's say the negatives of each process. Did a little overall comparison with them. And so as we wrapped up that webinar, we had a bunch of good questions about process improvement and post-extraction refinement processes. And so I figured it'd be a good topic to just continue on that train of thought and jump into kind of some of the more advanced post-extraction refinement processes that have developed over the years for cannabis extraction. I think most of you in the webinar know who I am, but if you don't, my name is Xavier. I'm the outside sales manager at Hal Extraction. We've been in the industry for about 7 years now, working in everything from retail to extraction. Unfortunately, I've got a black thumb and I've never made much of a stride in the cultivation side of things, but fairly well experienced everywhere else. And so we've been doing these webinar formats to help share a little bit of, not only my knowledge, of course, but my team's knowledge here at Hal, and give back to the community a little bit in this time of need as we all deal with the global pandemic, other issues in the world, and try to keep our heads on straight and get to work and get work done as we normally would. Hal Extraction, I do want to take a second to introduce the company. Again, I'm sure most of you here on the webinar know who we are, but if you don't, and if you're listening to this as recorded version, what we are is a group of extraction and cannabis industry experts, along with a group of very talented engineers that have come together to create solutions for cannabis extraction processes. Our core products are going to be extraction booths, Class 1, Division 1, Class 1, Division 2 booths, and kind of some other ancillary things relative to the extraction process. And so a lot of the time coming to us for pre-designed and pre-manufactured, prefabricated booths is going to be a cheaper route than doing your own facility design and going through the headache of having custom builds approved by local jurisdictions and things like that. So we can help a lot when it comes to initial approval process, but also reduce headache and reduce costs when it comes to initially setting up your extraction operation. We've done a couple webinars already, so be sure to check us out on social media or on our website for recordings of those, and be sure to subscribe and follow our main business page on those social media channels as well to keep up to date with any future topics and updates coming from the HAL team. All right, so today we're going to talk about two things really: the post-extraction refinement processes, and then some process improvements that have developed over the years, specific to hydrocarbon extractions really. I wanted to take today to focus on hydrocarbon because most of the questions last time were about those processes, and so we'll focus on that. And then I know I've been promising some guest episodes in the future, and still have those on the docket where we'll bring in some subject matter experts from specific fields that can help shed some light and get into a little bit of a deeper dive on other processes like supercritical CO2, some of the post-extraction refinement processes we'll discuss today, and other areas of the cannabis extraction process that may seem a little inaccessible if you don't have the right background. My goal here is really to make the whole process as easy and at least appear relatively straightforward to anyone that's listening to this podcast. So it's a good basis to start with your knowledge of extractions, and should provide a good basis for those future deeper dives into the processes that we're discussing today. So post-extraction refinement, why do we do it? What's the end goal here? What do those processes look like? Really, post-extraction refinement, as the name would allude to, are processes that aim at refining your crude extract. So the extraction crude oil that you're getting out of your closed-loop systems, your supercritical CO2 machines, your ethanol vessels. So it aims to take that initial crude extract and then refine it into more consumer-friendly products, either to eventually make it into things like edibles or vape pens, or just to make better dabbable vaporizing concentrates from the get-go. A lot of time, the solvents that we use, ethanol, CO2, and hydrocarbons, while they're very effective at extracting terpenes and flavonoids and cannabinoids and the desirable, let's say, products from plant matter, they're also very proficient at extracting undesirable things. So chlorophyll is water soluble. Sometimes that can get into your crude oil. Obviously, there's a lot of lipids, waxes, essentially fatty acids that can find their way into your extracts. And so the post-extraction refinement process is designed to remove those and give you a higher purity concentrate that you can then effectively dose into your final products and make a very consumer-friendly product. I do want to say that the extraction process you use is going to affect the amount of lipids and undesirables that you get in your final or your initial crude oil. So cold ethanol washes, for example, typically will lock out the most lipids from your final crude oil, so those will stay in the plant matter. Whereas CO2, because you're essentially using shearing forces to brute force out those cannabinoids and terpenes, a lot of time you're going to bring a high quantity of the undesirable products as well. And then hydrocarbon kind of falls right in the middle. But hydrocarbon, and we'll get to this later, does have the added benefit of developments of technology like inline dewaxing that can help prevent those lipids from making it into your crude oil. So to kind of continue on that premise, I like to think of post extraction refinement as really enabling you to be almost like an alchemist of old, or of lore, where you're taking something that might be undesirable, trim, biomass, and then through these chemical processes, you are able to achieve a highly desirable end product. And so let's demonstrate a little bit in these pictures here. We can see on the top left a crude ethanol extraction. It's got that green tint to it. I know not everyone in here has actually worked in a lab, but I can almost smell it's like a planty alcohol mixture. Not something desirable, definitely not a product you want to be directly consuming. But through processes like decarboxylation, which we see on the top right, essentially off-gassing our carboxyl group from our THC, to convert to THC, and then through dewaxing, like we see on the bottom left there, we're able to then distill isolated cannabinoids and products out of that crude oil and get something really nice and pure like we see down there on the bottom right. So, that crude oil may start at the 40 to 60% THC range, whereas with that final distillate, you're looking at something that's typically going to be 95% higher. So again, very effective for dosing your edibles and making sure that your vape pens are filled to the advertised milligram level and THC percentage. So I figure we could start with winterization. I do think winterization is kind of one of the most basic post-extraction refinement processes. It's been around since, essentially cannabis extracts themselves have been. And what winterization does is it really serves to remove these lipids and waxes I've been talking about. And it does so by coagulating them in kind of cold temperature, cold ethanol washes, and then using filters to actually remove those from your crude oil. Why we do this? Well, I'm sure people here have smoked vape pens before and tasted a very acrid kind of burnt flavor. A lot of time that can happen if your lipids are clogging up your vape pen or collecting on the coil of the vape pen itself and burning off of that heating element. Or similarly, if you ever purchased shatter, the BHO concentrate, and then after a week or two, it all of a sudden has turned into wax with the process of nucleation, and the lipids contained in that initial shatter are what are causing that nucleation to happen. And so we really want to get those out of our consumer-friendly products as much as possible. And so how does winterization work? Well, concept is very simple. You're taking a non-polar substance, in this case our cannabis and concentrate extract, and then we're dissolving it into a polar substance, in this case ethanol, and then again chilling it to separate those waxes and lipids at sub-zero temperatures. So what we do is take the crude oil, suspend it in ethanol. Typically, you're looking for about a 1-to-10 ratio of volume for that solution. So, if you have 1 liter of extract, you want 10 liters of ethanol. Then after mixing that, you can use a stir plate, for example, or just kind of physically agitate it so you get a good homogenized mixture there. We're going to take a chiller, and this could be a walk-in freezer, kind of a sub-cool freezer. But something that's going to get very cold. We're looking for temperatures that are ideally as close to negative 80 degrees Celsius as possible. But anything below negative 20 degrees Celsius will suffice in a 24-hour time range. And so there's a balance of production capability and throughput here, along with having access to specific tools. Obviously, the more expensive chillers are going to be able to help you achieve those lower temperatures, but there sometimes has to be a balance and kind of that tightrope walked between the price and the efficiency of your operation. And so once the solution with the ethanol and the crude oil has been chilled for about 24 hours, those waxes will actually start to precipitate out of that mixture. So you see them start to coagulate. The mixture may get cloudy. You can even see a layer of separation between the ethanol and crude oil and the lipids, forming a layer on top. But essentially what's happening is those fats are coagulating to each other, and separating out of that liquid. And so once you see that start to happen, that's when you're ready to actually filter those waxes out. And so you can take that mixture. You can see on the image here, this is actually a demonstration of a Buchner funnel. So we have a little filter, probably a paper micron filter that's placed at the bottom of this white funnel at the top. The crude oil, you can see on the kind of left half of the picture there, is poured into that container. And then over time, either through gravity or vacuum assisted pumps, you'll pull that solution through that filter, and the lipids, which you can see on the right, will begin to collect on that filter. For best results, I typically advise that folks actually do multiple passes. You want to start with maybe a higher micron filter, move to something a little bit more in the medium range, and start with and then end with your finest filter to really catch kind of every lipid molecule in that solution. Again, the pure solution that we get, the most lipids that we remove from it, the better it's going to be for your final product formulation. And so once this has happened, the winterization is complete, and the next step is really going to be to actually remove that ethanol you added back into the solution out of your crude oil. And so you could do that through distillation, use rotovap, and we'll touch upon distillation today. And so that's usually a good process to actually separate the ethanol from the crude oil. All right, so the next process I want to discuss is dewaxing. Dewaxing, as the name alludes, is actually very similar to winterization. They're achieving the same purpose here. The idea is to actually remove those lipids from your concentrate. However, dewaxing is different than winterization in that it actually happens during the initial extraction process. Whereas winterization is definitely post-extraction. It requires the addition of ethanol as a solvent kind of solution, and the time required to actually help coagulate those lipids. Inline dewaxing does all that directly in your closed loop system. And so the main differences here are going to be the solvent used. Obviously, if you're in a closed loop system, you're going to be using hydrocarbons, typically butane. And again, this happens in your closed loop system as opposed to after the extraction has already happened. So dewaxing works in that you take your initial extraction, so you pass your solvent through the plant column, and then there's actually going to be a secondary vessel in your closed loop ecosystem where the dewaxing occurs. Typically, this vessel will be jacketed into a chiller. The entire apparatus actually might be a walk-in freezer, for example. But the idea is to get that vessel down to those sub-zero temperatures. So again, ideally as close as possible to negative 80. It's a little bit harder, to Celsius, I should say. It's a little bit harder to achieve for dewaxing. Obviously, it's hard to kind of put the entire unit in a sub-zero freezer. But if you're getting below negative 20 degrees Celsius, you're going to see some good results from your dewaxing. And what happens is, as the butane or hydrocarbon mixture, along with those cannabis extracts, sits in that dewaxing chamber, the same process occurs. So the waxes start to coagulate. They separate out of that mixture. And then as you can see on the screen here, what you can essentially do is pass that mixture, the super cold solvent and cannabis extract, through a series of filters, typically following the same philosophy where you start with a higher micron, coarser filter before moving into a finer, whereas displayed here, an absolute filter, to remove those lipids from your products. And so this kind of leads to other developments in hydrocarbon extracts that we'll talk about later, where folks are starting to use really cold environments to actually go through extraction processes. There's a number of benefits of doing so, the main one being dewaxing and your ability to actually remove these waxes from your extract prior to getting to that final step. So I think between winterization and dewaxing, they're both very similar. Winterization is nice in that it doesn't require a specific solvent process to conduct. It can be used universally with all kind of initial extractions. But of course, there's the added convenience from dewaxing of actually having this occur in your closed loop system prior to you pulling your final extract solution out of that closed loop. So the next important process, post-extraction process I want to talk about is decarboxylation or decarbing. This might be the most important post-extraction refinement process because it really allows your edibles, if you are in the edible production field, to actually be potent and get your consumers high. Some of you may know this, but all plant-created cannabinoids, the cannabinoids that exist naturally in the plant, they all have an extra carboxyl ring in them. Sometimes that can be fine. It doesn't affect our body's ability to interact with those compounds and to bind to cannabinoid receptors. But sometimes, in the case of THC and THCA, it actually will prevent us from locking into those cannabinoid compounds and having them affect us. And so decarboxylation is the process of removing that carboxyl group or carboxyl ring and converting your THCA into THC to make it psychoactive. So again, for products like edibles, some vape pen companies prefer to do this, but you really want to have your THCA converted to THC so that it is readily psychoactive and can bind with cannabinoid receptors in the consumer's body. So two things cause decarboxylation to happen, either heat or time. You can think about smoking a flower, for example. You're actually applying intense amounts of heat, of course, to it as you light a bowl, which causes the THCA to then decarb and convert to THC as you inhale it. And then you can also see sometimes if you look at test results in flower that you buy at a store, for example, there will be trace amounts of THC because actually over time the THCA will degrade. That carboxyl group will off gas and it'll convert to THC. However, in a production environment, we don't have time to wait for that to happen. And so we're going to use heat to actually force the reaction to happen here. One thing to know is that heat will not only cause this decarboxylation to occur, but also can potentially compromise the integrity of other compounds in your extract. So things like terpenes and flavonoids typically are a little bit more volatile than cannabinoids, and so they will actually be compromised at lower temperatures. They may off gas from your solution, and so we want to take an approach that balances achieving the decarb process while preserving those other more volatile compounds in your extracts. Of course, you don't want to just off gas all of your terpenes and have a flavorless concentrate. And so carboxylation typically begins to occur around 220 degrees Fahrenheit. There is some time involved there, about 30 minutes usually. And so once the solution is heated to that temperature, the THCA will actually start to decarboxylate, will convert into THC. You can actually see some agitation in your solution usually. So it almost looks like it's boiling as that CO2 is escaping the main solution and off-gassing into the atmosphere. And then what happens is that slow conversion to THC. And so once you give it a little bit of time, I like to think, around 2 hours usually for a solution. Of course, this will depend on the volume and the weight at which you're decarbing. But once that's happened and that bubbling has effectively stopped, most of your THCA will have converted to THC. And so you can perform tests to actually test the concentration of the THC there and make sure that you are decarbing the entire thing. Because if you are using edibles, you want to, again, have the highest dosage possible for not only formulations, but for that end consumer product. And so as far as equipment goes, for decarboxylation, I advise folks to do this in a rotovap because you have the spinning element. So you have a thin film of your crude solution that's traveling up that flask wall, which, of course, the thinner solution improves the off-gassing rates and the speed at which you can actually decarb your entire crude oil solution. And just having something that has a consistent heating source. I think a lot of cheaper lab products will have a varying heating source where you set it at, let's say, 220 for this process. And what it'll actually do is spike up to 320 or 350 or 300 for a couple seconds, then turn off, and kind of have this varying spiking, variance between spiking off to a very high temperature and being off. And so when it does spike, you run the risk of compromising the integrity of those delicate compounds. So you want to find something that's high grade that will maintain a consistent heat within a 2 degrees, the temperature you set it at, to prevent any of that compromisation to happen. All right, and so now we have removed our lipids, and we have converted our THCA into THC. And so the next process I want to discuss is actually removing that THC from the rest of the compounds that might be present in your crude oil. Well, actually not just THC, but basically isolating compounds from the rest of the crude. So it could be THC. In some cases, you might be able to isolate specific terpenes, other cannabinoids. For example, if you're running CBD products, you obviously want to remediate the THC out of it, so you can isolate the CBD from the THC. But essentially, what we're doing is isolating specific compounds from each other through distillation. I will talk about thin film or wiped film distillation right after this, but I thought we'd start with short path. Short path is typically, I think, the more accessible as far as cost and kind of understanding, chemical understandings go, but certainly less efficient method of distillation. So we'll start here, and then we'll move on to the more complex one after this. So starting with the image on the right here, I was able to find this on the internet, and I think it's going to be a great tool to walk through the different components of distillation. And then we can kind of discuss how the system operates as a whole. And so the basic concept of distillation, again, is to isolate compounds. And we're going to do that by actually creating a very specific environment inside of our system by controlling the pressure and the temperature present in that system. I don't know if you remember in kind of basic entry-level chemistry, but different elements have different atomic weights. They combine molecules, different molecules have different weights and sizes. And the weights and the sizes of molecules actually affects the temperature at which they boil or they turn into gas. And so what we're doing here is by narrowly controlling that temperature that's present in the system, we're able to specifically target certain compounds, have them essentially evaporate out of our main solution, move through the system, condense back into a liquid, and then become isolated over to the right. So let's actually look at the components here and walk through that process. So starting on the bottom left of this image, we're looking at the image on the right, the diagram. You can see the numbers there. So number one, it's just a hot plate. We've got our starting flats, number 15, and it's in a little bit of a hot water or oil bath. It's that golden liquid right there. What that does allows for even heating amongst the entire bottom of the flask. We do want to use a round bottom flask here because it allows for greater surface area, which translates to more even heating of that solution inside of it. You can also actually add kind of rotating mechanical assistance here to turn that, similar to what you see on a rotobath, which again will promote even heating and a greater surface area for evaporation of certain compounds out of that crude oil. And so the gases that evaporate out of that crude oil there are going to move up into what's called the Vigoro column. And that's what this little glass tube is above the main flask with the little fingers. And what the Vigoro column does is actually encourages the condensation and trapping of heavier molecules. So it's actually acting as a little bit of a filter. We're stopping those molecules from evaporating off along with our desirables and keeping them contained within that environment below. So controlling which gases are able to actually escape from our main solution. Then we do have a thermometer up there at the top, kind of checking the temperature at the head of the Vigoro tube there. That's a very critical point in the process because it's going to define which gas or which compound, I should say, remain gases at that point, and we'll be able to travel past that. So you really want to control temperature right there. That might be the most critical temperature control point in the entire system, even more than the crude oil bath that we have at the bottom. And then following the path through the system here, what actually happens is we have a chilling or kind of condensing jacket. So you can see the water inputs or the chilling fluid inputs over here on 5, 7, and 6. And what's happening there is the vapors that are then off gas from our main solution will condense back into liquids as they're chilled. And then what they'll do is they'll drip through and down into 8, or our collection flask, which is also sitting in a little bit of a chilled liquid. And they'll condense through there, collect there for you to be able to collect those at the end of the process and have isolated compounds. 9 would be a vacuum line. So we see a little vacuum line going off to the right. A lot of folks will typically have another cold trap there just to ensure that no unwanted compounds and vapors are making it all the way into your vacuum. You obviously don't want to compromise your vacuum. But that's essentially what a short path distillation system is. And so this entire system here is going to be under pressure, typically as low as you can go. At sea level, we're looking at negative 29 inches of mercury. We're in Colorado, so sometimes I remember only being able to shoot like 26 inches, but you want to go pull as deep a vacuum as possible, which again allows you to boil off these compounds at lower temperatures, preserves the integrity of those compounds, and means that you won't be dealing with any nasty terpenes, for example, because terpenes will off gas at a lower temperature than your desired THC. If you get that mixed in with your THC that's been isolated, you end up with a mixture of highly pure THC, but very undesirable product, because it does have that burnt terpene profile inside of it. So you want to make sure that you're controlling your temperature and your pressure to really isolate the compounds that are being off-gassed and then being recollected in your collection flask. And the image on the left here is just meant to show what this looks like in action. So about a 1-to-1 kind of image here, except for that we do have this middle collection flask. Actually, no, that middle flask is for collecting the compounds, and over there on the left, or on the right, sorry, we can see that final ice trap to ensure that nothing's making it into your vacuum. All right, so on to short path distillation's big brother, thin, wiped, or falling film distillation. These are all different names that essentially mean the same thing. Really what's happening in this process is that we're doing the same thing we did on the short path distillation, but we have mechanical assistance to help with our evaporation rates and just greatly increase the throughput through the system. So when it comes to production, if you're generating a lot of, or looking to generate a lot of distillate, a thin film system will definitely be the right way to go. So here what we're looking at, and we've got this middle cutout. It might be a little hard to see. I'm not intending for everyone to be able to read the words here, but it's more just a diagram to show you what we're looking at for this gentleman on the left. What we have is on the top right, where that dark brown liquid is, you can see it even better on the image on the right here. We have our starting crude oil. And so in a thin film or wiped film system, that actually starts above where the distillation is happening. And then the oil, or the crude oil, will actually drip down into the wiped film column. And so I think I really want everyone to pay attention to the image on the right here, which shows well that crude oil dripping down into that. And then inside that column, what happens is we have either wiper blades or the column itself is spinning, so we're taking advantage of centrifugal force to spread a very, very thin layer. We're talking 5 microns maybe of crude oil on the interior, the interior exterior, the interior outside interior surface, I guess it would be. Essentially the outside wall inside that column. And so there's a very thin layer of crude oil on that. And then there's actually going to be a heated jacket on that column that will encourage the evaporation of those specific compounds off of that crude oil. And so we're doing the same thing here that we did in the short path, just doing it a little bit more efficiently. And then what happens is in that thin film column, the wiper column or centrifugal force column, whatever you want to call it, there's actually going to be a chilling element, a chilling finger going right in the middle. And so that's demonstrated again on the right. You can see the blue, almost like screw-looking piece right in the middle. And that's actually going to be chilled to, again, condense those evaporated compounds back onto that core piece of the thin film tube flask, and then actually drip down to a separate flask at the bottom than the rest of the crude oil and the undesirables will drip into. So again, same process here, just a little bit more efficient because we have that mechanical assistance to spread this initial solution into a much thinner sheet allowing for increased evaporation and increasing your efficiency. The other benefit with thin film systems that we'll actually be able to take this starting compound, so the flask up on the top right, and we can actually remove that. Basically, there's vacuum interlocks, so we can close the vacuum system, keep the entire system under pressure, remove that flask, and then add another one while the distillation is still occurring inside of your system. So there's the ability to kind of have seamless 24/7 production if you have enough crude oil lined up to where you can just kind of be swapping these flasks in and out. All right. Those are the processes I want to touch upon for the refinement piece of the presentation today. And now I just want to move into talking about process improvement specific to hydrocarbon extracts. Do want to discuss some specific product formulations? So, comparing wax, shatter, and diamonds, and kind of how we achieve each of these consistencies. And then I do have a quick slide on how your solvent quality choice will actually impact your final product. As anyone can imagine, the quality of your solvents that you use to extract your cannabinoids can have a very big impact on the quality of the actual extracts that you're getting from your plant material. So starting with hydrocarbon process improvements, the first one I want to start with is very straightforward. It's active solvent recovery. So typically closed loop hydrocarbon systems exist in really two kind of main categories. One of those is going to be passive recovery, the other one's going to be active recovery. Passive recovery takes advantage of thermodynamics and the properties of gases, to where you have your initial solvent tank is typically going to be like a hot water bath. The heat applied to that tank will cause the gas inside of it to expand, increasing the pressure in that tank. Then that gas, of course, will seek the path of least resistance, typically through a solvent line, into your closed loop system. And so you're moving the solvent from the tank into the system. And then conversely, your recovery tank is going to be placed in a cold water bath, which creates that negative pressure differential, will encourage the solvent to move through the system, and allows you to recollect the solvent after a run in your collection vessels. After, of course, you have removed the cannabis extract from the closed loop system. And so active recovery is pretty straightforward in that it adds a pump into that process. So instead of necessarily just relying on the pressure differential between the hot and the cold solvent tanks, you can actually have a vacuum pull the solvent through the system, which can cut your process run times down by a factor of half sometimes, moving from, let's say, an hour and a half to 45 minutes. I think passive recovery is not very efficient because as you heat up that initial solvent tank, of course, as the gas escapes from it, it's going to conversely cool down the tank, slows down the process moving forward. You get kind of a negative feedback. So active solvent recovery adds a pump into the process to actually pull the solvent through the system. You can use the pump to actually create a negative pressure differential inside your system before you open your solvent tank. The solvent will then flood the system quickly. You let it saturate, you pull it out, and then you can use the solvent pump to recover your solvents. I do want to say, because there's always a little bit of safety thrown into our webinars here, very specific types of pumps are required for this. You do not want to use a typical vacuum pump that is either electronic or mechanical. Instead, you want to use a pneumatic pump that has no capabilities to spark or actually ignite the hydrocarbons that pass through it. A little bit more expensive, but if your goal is to have the most efficient process and have the highest throughput possible for your closed-loop system, the cost will be nominal to the eventual gains you get through that increased processing capability. So the next process improvement kind of goes hand in hand actually with active solvent recovery. This is nitrogen-assisted hydrocarbon extractions. This is something that we had a couple questions on with the last webinar, so I do want to dedicate a slide to that here. Nitrogen assist is where you use nitrogen, which is not an inert gas, but for all intents and purposes, for this process, it acts as an inert gas. It will not interact with your hydrocarbon that you're using to extract your cannabinoids. It won't mix with your cannabinoids. It essentially stays a separate compound inside your closed loop system. And so nitrogen, what happens here is after you've gone through your extraction process, you have a nitrogen tank. You can see that in the diagram here, the nitrogen gas over there on the top left. And what happens is you'll open a valve and release the nitrogen into your system. That nitrogen then creates a wall of pressure that moves through the system. Nitrogen is typically stored at a much higher PSI than your hydrocarbons are, and so there's a lot of pressure behind it. So it effectively will push your solvent and your cannabinoid extracts through your closed loop system, allowing you to recover that solvent and allowing you to finish your runs a lot quicker. And so a combination of nitrogen and active solvent recovery goes a long way as far for improving your process times. Now we're down to like 30 minutes, let's say, depending on the size of your system. The nice thing is that because nitrogen is effectively an inert gas for this process, you don't have to worry too much about contamination with your solvent. Obviously, you want to time your nitrogen releases properly. You want to be weighing your recovery tank as you are filling it with hydrocarbons for your system, so that once you achieve the same weight that you had in your starting tank, you can shut the valves off and make sure that not too much hydrogen is making it into those solvent tanks. There's a good chance that some of it will, but it's not the end of the world because it's not going to reduce the quality of that solvent for the next runs. From a safety perspective, it is important to note that nitrogen, because it is stored at a higher pressure, it will increase the overall pressure contained within your closed loop system. So it's very important to make sure your system is rated to contain nitrogen. We're talking closer to 150, 200 psi, whereas hydrocarbons might be running closer to 100 psi. So really making sure that your pressure vessels are equipped to handle that added pressure is going to be key to making sure this is a successful process for you and that no one gets injured. All right, so fresh frozen. This is going to be a little bit of a continuation of what I talked about with dewaxing. But I think this has kind of been one of the more impactful process improvements that we've seen over the last decade specific to hydrocarbons. I'm sure everyone here has heard of live resin. And live resin is created from fresh frozen product. And so what happens with the cannabis plant is heat, time, light, all these variables will come together and actually degrade the compounds in the plant, will convert, again, we talked about THCA to THC, could potentially compromise the integrity of your terpenes. So what people have started to do is actually take their freshly harvested plant matter, they'll put it into a vacuum bag and actually seal the vacuum on that, pull it down, so there's no air contained within that bag, in that environment, and they'll freeze it. And by doing so, what we're doing is effectively stopping that degradation process, stopping the cure from happening, if you will, to the flower, and locking in the initial essence of that flower as it's been harvested. So the initial flavors, the initial terpenes, and of course the initial cannabinoid content of that plant matter. Freezing it will actually also lock out water, which is an important thing to note during the extraction process, because you do not want water to make it into your final extract solution. That will cause the nucleation that we discussed earlier, and it'll just make for an inferior product. Not to mention kind of reducing the quality and the potency of your THC in there. And so by locking out the water into ice crystals, we force that to remain in the plant. The hydrocarbons will not interact with that water, and they'll basically just touch the cannabinoids and desirable compounds. And fresh frozen ends up leaving a lot of the undesirables in the plant. And so the fresh frozen evolution has led us to have, kind of more potent, but also more terpene-rich and flavonoid-rich concentrates, which of course are more desired by the consumer. And so a lot of folks now actually will dedicate their entire harvest to be frozen to turn to extracts because it is such a desirable product by the consumer. Important thing to note is that once you freeze the plant, you want it to remain frozen. Again, keeping that water in crystal form is going to be key to the quality of your extract. And so a lot of folks that extract with fresh frozen product, what they're doing is they'll, let's say, fill up the column in their closed loop system with their frozen plant matter. Then they'll actually chill that column in a sub-zero chiller, something you might use for winterization, for example. They'll chill in there, get it nice and cold, or have a jacketed column with attached to a chiller that will actually keep the column cold as you process the solvents through it. So you want to make sure that everything's staying below that zero, below the 32 degrees Fahrenheit, 0 degrees Celsius, to ensure that water remains frozen and that we're able to keep it out of the extracts. And so that's what fresh frozen does, and that's kind of where the live term comes from. When it comes to live resin, live butter, those things. We're kind of getting close to the end here, so I don't want to talk too much about the cold trap terpenes. This is a little bit older of a technology that I think people are moving away from, so I'm not going to spend too much time there. But I do want to discuss mixed gases. Mixed gases have been a pretty significant improvement to hydrocarbon extracts because not all hydrocarbons are created equal when it comes to what sort of compounds they're actually going to be interacting with in your plant matter. Some hydrocarbons might be a little bit more efficient, like in butane's case, at extracting cannabinoids, so you typically get a higher potency when it comes to THC extract, but might not be quite as efficient as propane in extracting specific terpenes. So by using a mix, you can actually accomplish kind of a greater spectrum of desirable products in your extract and can replicate the entourage effect of the initial plant matter a little bit better. Now, of course, do have to say, don't use benzomatic, don't use Calibri butane. These are just images to show propane and butane, but these are not the type of solvents you want to be using during your extraction process. But what folks have started to do is actually use mixed gases. So typically 70% butane and 30% propane tend to be kind of the go-to mix to achieve that balance of maintaining a high potency, extracting a lot of cannabinoids, but also getting some of those terpenes in there to get a little more of a flavorful product. Kind of anecdotally, propane extracts tend to have a little bit of a lighter color, so it might be a little bit more appealing visually. So using a mix like this can end up really benefiting your end product. I do want to say that some folks use entirely propane. I think that's not the best approach because you are extracting a high number of terpenes. Terpenes, as I've said a couple of times, are fairly volatile compounds. So it's really hard to get a stable final extract when you're using propane. Your shatter, for example, will remain very, very sappy. Your waxes may never coagulate into wax. And you're going to be left with something that's not as consumer friendly as if you had a mix or if you have just pure butane. So I think that 70-30 balance is really kind of the industry standard and will give you the best final product. All right, so the last few things I want to do is actually walk through some of the different products and how to formulate them. I'm going to talk about most popular ones, so shatter, wax, and then diamonds. So starting with shatter here, this I think was the most popular extract for a while. Has now taken a backseat probably to diamonds or live resin. But good shatter is still definitely a consumable or a consumer desired product, and a lot of folks make good money selling their concentrate as shatter. And so shatter is a very straightforward process. What you do is you take your hydrocarbon extract, and then before it's ready to go, you're going to need to essentially off purge residual butane or hydrocarbons that are trapped within that sappy mixture. And so you'll take your hydrocarbon cannabinoid solution out of your closed loop system. You can pour that then into a thin sheet, typically on a piece of parchment paper. And then you place that into a vacuum oven. And what will happen is the vacuum will actually pull those remaining hydrocarbons out of your solution. And as it stabilizes and as those hydrocarbons are pulled out, what happens is the concentrate turns hard, takes on a glassy appearance and consistency, which is why it gets the name shatter, and will stabilize into this consumer-friendly product. The vacuum oven temperature is an important thing to consider during this process. I think typically you don't want to go too far over 105 degrees Fahrenheit. That may cause your shatter to begin to nucleate and turn to wax, and it will never get to that stable point that you want to see, where you can really just kind of take a piece and snap it, similar to you would be able to do with glass if you were to drop on the ground. You can see that shatter, hence the name. This is where dewaxed product also comes into play. You don't want any additional lipids or waxes. I know it's confusing. I'm saying dewax and wax. And so there's the product wax, but there's also the lipids and the waxes that come out of your plant material. And so for this, you want to use a dewaxed initial concentrate to prevent any cloudiness or nucleation to happen inside your shatter. The consumer is looking for clarity. They're looking for color. So light amber color typically is preferred over darker orange. And they're looking for that consistency. So as hard as it can be, and kind of as shattery, there's not really any other way to say it. It's going to be better for the consumer. If you are having issues with the stability, there's a good chance there might be other compounds present. I've seen in the past folks using specific pesticides and garden chemicals in their flour, which are then extracted through the extraction process and affects the consistency of that final shatter. So you might want to look at your starting product a little bit. Modifying your gas blend can also help. So using a little bit more using a little more butane over propane to increase the cannabinoid content versus the terpene content. There's a couple different ways you can approach really improving the consistency of your shatter. And it kind of comes down to each specific process, especially with the starting plant material that you're using. All right, so wax is another form of hydrocarbon products that folks are dabbing. Wax, again, is a little bit of a confusing name. We've been talking about lipids and the wax from your plant. This, of course, is not that. So we're not just removing those lipids and then repackaging them as a dabbable product. People would not be too happy about that. Instead, what we're doing is taking that initial hydrocarbon and cannabinoid mixture that you're extracting and taking out your closed-loop system. And as opposed to putting it in a vacuum oven like we would for shatter, what we're doing is we're keeping it in a little bit of a thicker container, or not thicker container, but keeping the thickness, let's say, of the mixture a little bit greater, so you're not spreading it super thin. Usually in a Pyrex dish, you have about an inch or half an inch, let's say, of that mixture present. Then you're applying heat and agitation. So by taking, let's say, a stirring tool and physically agitating that wax or that mixture, what happens is not only is the remaining hydrocarbon going off gas, but it will begin the coagulation process with the heat applied to the mixture. That causes it to start to cloud up, start to firmify, and turn into wax. And so over, let's say 45 minutes to an hour, physical agitation and that whipping and then applying it to heat, what happens is the cloudiness starts to form and you get a little bit more of a crumbly honeycomb texture. And then once you see that start to happen, what you can do is finish it in an oven, not under vacuum. And what happens there is it'll dry it out, it'll de facto bake that mixture into a harder consistency, and you end up with wax. I think culturally, wax is less desirable than shatter. I think it really comes down to personal preference, though. I've found plenty of waxes that I think are far less superior to shatters that I've had. So it's good to offer a balance of both. And I think what a lot of companies do is they look to wax as remediating a concentrate that they started as shatter. They weren't able to achieve, let's say, the desired consistency. So then they repurpose that as wax. So I think that's where kind of the anecdotal, let's say, approach to thinking that wax is less desirable than shatter comes from. But really, I think it comes down to personal preference. All right, and the final product I want to touch upon, and kind of the say the newest product of the scene, and kind of what folks are really hyped about right now, is going to be diamonds. So you see this referred to as crystals, diamonds in sauce, live resin, which is a little bit inaccurate to call it live resin, although it does use fresh frozen. Um, but this is kind of the new most desirable, let's say, consistency of hydrocarbon concentrates. And you create hydrocarbon diamonds or cannabinoid diamonds the same way that diamonds are created in nature, so through pressure. And what we're doing here is taking that initial mixture from your closed loop system. So you have your residual solvents in there, but you also have all your cannabinoids, your terpenes, desirables. And you're going to place that inside a sealed container. And then over time, what happens is as those residual hydrocarbons are off-gassing from that mixture, they increase the pressure inside that vessel. The pressure will then force the cannabinoids at the bottom to begin to coagulate, crystallize, and form crystals. What you can do to increase the speed of this process and the efficiency of the process is actually use gases like nitrogen to increase the pressure inside that vessel and allow those crystals to form easier. And so once that's completed, what happens is you have a mixture of your cannabinoid diamonds along with typically the other components like the terpenes and the flavonoids that remain a viscous liquid. So you'll have your diamonds, and then you can pour off your terpenes and separate them, and either put them on the shelf for the consumer as just the pure diamonds like you see on this image here, or I think a lot of folks prefer to actually reintroduce the terpenes and have a bit of a mixture of the terpenes, the cannabinoid diamonds, so you're getting that nice flavor profile, while also still being able to get nice and high. Disclaimer here, I see a lot of folks online suggesting, mason jars, things like that. I don't think that's a good idea. Mason jars, glass, and under pressure, over time, that basically turns into a little butane or hydrocarbon grenade. That can be very dangerous. I've seen plenty of mason jars explode under pressure, and you got glass shards and concentrate flying all over the place, which is not only dangerous, but can be quite a pain to clean up. And so I think using a pressure rated vessel is the best way to go when it comes to creating diamonds. All right. So last slide here. I know we're right at the top of the hour. So I think this is kind of a read through slide. There's not too much to talk about here. It's fairly self-explanatory. But the quality of the solvent that you're using in your extracts does matter. So when it comes to hydrocarbon and butane, you want to be using N-butane, not isobutane. Isobutane is typically reserved for lighter fluid. There's adulterants added in there. Lubricants are added in there. And other things that make your lighter work better. But of course, you don't want to have that in your cannabis concentrates. So you're going to be looking for UHP or HB, that stands for ultra high purity or high purity N-butane. And then we have 3 different grades of butane: research, instrument, and refrigerant. You want to be looking for research grade butane. That's typically reserved for food products, using consumables, basically any product that might end up inside a human body. Instrument and refrigerant grade butanes, of course, have other compounds in there that help those machines run better. But again, not compounds that you want to find in your extract. And then for ethanol, you're going to be looking for 95% or absolute ethanol. Denatured ethanol has denaturants added into it to make it taste bad and make it unconsumable. So it doesn't have to be taxed as liquor. So it's a little bit cheaper. So you might be like, oh, hey, I want to use a cheaper ethanol. Don't do that. That'll add a bunch of compounds into your extract. It might be good for cleaning, but it's not going to be good for extracting. And then 95% absolute ethanol. It's a toss-up between the two. Ethanol is actually anhydrous, so it will attract water from the atmosphere. And if you get absolute ethanol, it'll eventually turn into 95% ethanol. So it's just a matter of whether or not you want to keep your ethanol capped all the time. I think 95% ethanol is typically what we use, but it's a little bit easier to find. And then the last slide here, we've got some sources. We did just recently team up with the Good Life Gang. They've got a forum called Future 4200. Check them out. They have amazing information on all of these topics. If you really want to get into the details, kind of how to actually apply these to your operations, they're good people to look at. Naughty, one of my favorite and kind of one of the earlier extractors to the team onto the scene. You can find him on YouTube. And then actually, equipment manufacturers tend to have a lot of great advice, not only on how to use their equipment, but how to actually go through the processes and create specific compounds using their equipment. So that's what I had for us today. Let's see if we got any questions. As usual, contact information's up here. Andy, yes, so yeah, this video will be available. Jamie on our marketing team has been collecting recordings of these videos, and so I think we're still working on the best way to send it. I think you do get a recording actually if you signed up for the webinar, so you should see that come through. And if not, just reach out to us directly, and we'll be sure to provide that to you via email. But all these will eventually make it up to our website, and we'll have a little section for webinars where you can see all the historical videos. All right, guys. Well, Jamie, Emma, Andy, Tony, appreciate all of you guys joining me today. Hopefully you learned a little bit. Feel free to reach out to me directly with any other questions. Check out those sources I posted. And if anyone is building a facility, come over to Hal and let us help you out. Thanks, guys.